In this video, I'm going to jump right past the monoprotic acids or bases being titrated, and we're going to talk about polyprotics because they're going to have all of the key features that we need inside of them, and it allows me to make some important distinctions. So very briefly, I'm going to go through the regions of a titration curve for a polyprotic acid with pKa for the first proton of 3.0, pKa2 for the second proton of 7.00, and pKa3 of 11.00. Now, if we start out trying to come up with our titration curve, and we're trying to come up with a way to describe each of the regions, we know that when we've added 0 mils of base, and of course this axis can be in lots of different things, but I'm going to list it in mils of base. When we haven't added any, we're just going to be doing a simple titration curve. So right here I'd say is going to be my region number 1. And at location 1, we can see that we're at our initial concentration. And if we set up an ICE table, we'll get, I'll actually write it out once. We'll have our first proton being dissociated. We'll have H3A becoming H2A minus and H plus. We do our ICE, and we'll keep it generic by saying it's formal concentration initially. Then we're going to lose some of this as X. We didn't have any of this initially, but now we're making some. So we end up having formal concentration minus X. Over here we're going to have plus X and plus X. So we're just going through our normal ICE table. And we're used to seeing this sort of a form. And we know that we'd end up having to solve a quadratic equation for this once we actually set it all up. And when we have our Ka expression, Ka equals, remember that it's going to be our products on top, so x times x, so x squared, over formal concentration minus x. And so we'll find this in the book as kind of our initial point. We're going to see something that looks a lot like this later in a titration as well. So our very first point will end up having that sort of an expression. Okay, and just cleaning that up so we have some space to work, I've gone ahead and just summarized it right there. Now, once we start that titration, we would go ahead and say, all right, and I'm just going to arbitrarily put a point on here. We would solve for it using our actual concentration. We'd solve our quadratic equation. We'd plug in our Ka, so 10 to the negative 3.00. Always be very cognizant of the difference between pKa and Ka. Don't let yourself fall in that sucker trap. Okay, so we've gone ahead and we've done that. We'd have our number pop out and we'd have our pH to mark this with. Now, if I'm doing the very, very fast and crude way, remember I said you can kind of go down about a quarter from where you have your pKa. So let's see, 2, 4, 6, 8, 10, 12, 14. That'll be enough pH markings. pKa for pKa1 is going to be 3.00. I'm probably safe putting that somewhere right around pKa of 2. And we know that we end up having the leveling effect, preventing us from getting much below pH of 2. Unless we're in a really concentrated solution. So we'd go ahead and we'd say, what's my next point going to be? Well, we also are aware that one of our key things we care about in titrations is going to be our equivalence volumes. So if it's triprotic, we're going to have to add a certain amount to get to our first pKa. Another volume that's going to be the same as the first, additionally. In other words, if I use 10 mils here, I'm going to use 10 mils here to get to pKa2. I'm going to then titrate my third proton. And again, I still have the same formal concentration. Now I'm working on that third proton. That'll be this region here. All these are going to be the same delta V's. So I'm just going to arbitrarily pick a number. I'm just going to say that it was 10 milliliters to get to there. That means my second will be at 20 milliliters. And at 30 milliliters, I will be at my third equivalence point. Now, when we set that up, this is probably going to be an easy one for us to start doing. So we want to have these intermediate points. Now, I want to point something out. We're going to have two different conditions here. For each of these two, we're going to have the point where we end up totally using up all of one form, but we're still in between two different forms. In other words, we're going to have an intermediate form. So for this one, we're going to have H3A. When we get to here, we're going to be working on H2A minus. Over here, we're going to be working on HA2 minus, and that's going to be in equilibrium with A3 minus. So I'll just write that way over here just to remind us, A3 minus. When I get to this spot, I'm going to be 100% in the form of H2A, H2A minus. I've stripped away that first proton from every one of my molecules in the formal concentration. But here's the thing. We also know that there's now going to be an equilibrium that has to form, where it goes from H2A back into H3A by picking up ambient protons. We're also going to have H2A continue to fall apart into A2 minus. So we're going to have to deal with two different equilibria simultaneously. And when we have that sort of a complicated case, we'd have to go solve our systematic treatment of equilibrium in order to get our full equation for it here in the middle. So let's go ahead and take a look at what that equation will look like. So for point number 2, what we're actually going to have is a correct way to do it and then a quick and crude way. Let me show you the correct way first to make sure you don't seize on the quick and crude, because that's only going to be useful as a quick benchmark. If you try giving it to me as a correct answer, that won't be correct. So make sure that you're using these two equations correctly. So when we actually have two different equilibria occurring simultaneously, if we solve the systematic treatment, we're going to get this. And rather than make you watch me draw it, I've gone ahead and written it in here. You can see here that what we care about is our equilibrium constant pulling it backward. Again, pKa, Ka. Make sure you're making that conversion before you start plugging it in. If you just start plugging in 3 and 7, you're going to be so far off with the correct answer with this. So make sure you're plugging the correct one in. Then you'll use your formal concentration. Notice that the next two things we care about are the first equilibrium constant and equilibrium coefficient of water. That's going to be over K1 plus F. Now, we could probably try to pick this apart and really try to get some sort of a broader conceptual understanding, but really, there's enough happening there that we can just summarize it by saying exactly what we did. In fact, let me fix that. Just that we have this equilibrium coefficient pulling backward, this one pulling forward, and so we're going to have that affecting our formal concentration, but more or less we're going to be having our formal concentration in this form, some of it popping apart in either direction. Now, rather than go through that derivation, we're just going to leave it at that. Now, if I were to go ahead and plug things in, I would get a concentration of H+, which I could then convert back into pH to put my proper number, which is what we should do. I'm also going to show you the quick shortcut benchmark that you can use when you're just getting a quick and dirty idea of what it should look like. This is not a solution, it is not a correct answer, but it's a quick and dirty benchmark. pH for an intermediate form is going to be in the ballpark, and I want to emphasize in the ballpark, of the average of the two K values involved. In fact, pKa. So we look up here and we say, all right, 3, 4, 5, 6, 7. So that's going to be 2 units apart. So pKa here, I'm anticipating that my pH at the spot halfway between them is going to be pH of 5. And so if we just needed a very quick and dirty point just so we can try to recognize a titration curve, we could use this. Now, before we get to that spot, we're going to have some base that we've added. We're reacting it with our acid, which means we now have some acid and its conjugate base, which means that for this whole region in between, we're going to step off just a little bit from the actual 2 points. So we have an appreciable amount of the acid and the conjugate base. For this region, we're going to have a third regime. And whenever you've got an acid and a conjugate base, I hope that you recognize immediately pH equals pKa plus log of the concentration of A minus over concentration of HA. And notice I left it in its most generic form there. And I'm going to point at this one and say the same sort of thing. What we do on all of these is we always make sure we update them with the two species we're actually talking about, the proton on form and the proton off form, the early K value and the late K value. And that's going to be a really critical piece here in a second. You'll see that exactly in 1 second. All right, so we have this number. Also point out, I'll call this one 3.A. if you're halfway between, so if you're the half-equivalence volume, this number equals this number because you've converted half of your original acid into its conjugate base. 50-50 mix, that means this value is 1. Log of 1 equals 0. And so at that moment, pH equals pKa. So if we just have to get another point to sketch very quickly, we can come right over and say pKa is 3. So halfway between my initial point and my first equivalence volume, I can place that in. Now, during this whole regime, though, we're still going to be having it act as a buffer. We know that pH will not change much in a buffer, even though I'm adding that base. So we should have something that's almost horizontal but has a slight slope because it will change the pH, just not a lot. So we can just kind of quick and crude go like this. It'll drop off a little bit when the buffering capacity is gone. Right here at the equivalence volume, the buffering capacity is gone as well, and it's going to suddenly shoot up. Now you can see that we've got our first section handled for our titration curve. Now what we need to do is stitch together a second and third segment, and then have a little piece for afterward. So I'm going to highlight something, though. In this next case, we have the exact same conditions occurring again. It's just that we're talking about two different Ka values involved. So I can go ahead and place my half-equivalence volume here at 15 milliliters by saying it'll be just like number 3. So this will be 3 and 3a happening simultaneously. pH equals pKa when I'm at the half-equivalence volume, which will be here at 15 mils. pH equals pKa would be 7 pH units. 2, 4, 6, 7. Come across. Put a dot in for that. And if we're doing a quick crude sketch, we just connect the dots with something that looks reasonable. But of course, if we're doing this numerically, we go ahead and we solve the buffer equation for a couple of different points in that regime. Or better yet, we model it in some sort of a numeric analysis program like Excel or MATLAB or something, and we get the actual range here. Now, we did see in previous videos that our buffering slopes are going to look different depending on how much concentration we've got there. We're assuming we have enough concentration here that we don't have to worry about the autoionization of water having a big piece of it. And we saw that when we get to low concentrations, we do have that concern, and our slope ends up looking much more steep. So we head toward our equivalence volume, 20 milliliters. You can see that I'm writing on a bit of a slope here, so this isn't to scale very well. At my next half-equivalence volume, I solve this equation, unless I'm just doing a very quick knee jerk, at which point I'll just use the average of my pKa's. I'm going to do the quick knee jerk, so I'm going to say 7 to 11. That's 4 pH units again. Average of that's going to be 2, so I need to go plus 2. I'll be at pH of 9. 2, 4, 6, 8, 9. So we're going to come right across to here. Oops. I went a little too far there, didn't I? We'll just ignore that. So that's where my next equivalence point would be. Now I'm going to do the exact same thing once again, buffer regime. So we say, all right, pK of 11. 2, 4, 6, 8, 10, 11. Remember that right around pH of 12, we're getting to the point where autoionization of water starts having a dramatic impact again. So if we are in this region, we're probably going to have a lot of leveling off on our curve. But if we're just doing a quick and dirty version, that'll work okay. For our last equivalence volume, though, we're actually going to have a different condition. In these two equivalence points, we're able to use this equation because we had two different K values to care about. Out here we don't. All we have now is pKa 3. This will be our final equivalence volume, which is going to have a slightly different equation than the others. So for our last equivalence volume, and this is true for monoprotic acids as well, in that moment we have completely converted our acid into the full base form. So this would be the moment where we've turned it to all A3-. So what's going to happen? It's going to start picking up protons from its environment, because now we're in the region where we have A3-. It picks up some protons, it's reassociating and kind of back titrating just a little bit, if you want to think through what's happening in terms of pH. So what we're going to do here is we're actually going to treat it as the same kind of problem as we had in our original moment. It's just now we're going to care about Kb. And remember, when we have a polyprotic acid, the first one is Ka1, Ka2, and Ka3. When we talk about Kb, this will be Kb1 once we convert it. This one converted will give us Kb2, and this one will convert to give us Kb3. We count in the opposite direction. So it'll be Ka from this number. So Kb will equal, we set up our our ICE table, we solve it, and we get the exact same sort of expression, x squared divided by formal concentration minus x. But I want to point something out. We have added 30 more milliliters. So we can't just use formal concentration anymore. We actually have to recalculate our actual concentration based off of that dilution. And here's where you can use a dilution factor to do that for you. This is true for monoprotics. This is true for our polyprotics for the last one. So we go ahead and we calculate our formal concentration. We can either get our Kb from that, or if we're doing a titration curve where we're given our Kas, we do pKa is 11. That means pKb will be 3, because remember 14 is the top of the scale, and we're just converting from the acid to the base form. So pKb would be 3. That would be pKb1. We convert that back, and that would be 1 times 10 to the minus 3 equals, and then we'd solve the rest of it. And that's what's happening all the way out here at point 4. Now, if I'm just doing a fast, crude one, like I'm doing today, I'd say, well, 2, 4, 6, 8, 10, 12. We know things level off at about pH of 12 in that aftermath regime. So I would go ahead and just kind of sketch it like this. We know that it's going to be a broader slope because we're so close to the basic end now that auto-ionization of water is making this a much more complex problem. And so we'd solve it like that. Now here in this last regime, though, what do we have? Now we're actually past that spot where we still had a little bit of equilibrium, pulling it back the other direction. Now it's really just a dilution problem. We go ahead and we take the excess amount of base. And so for that, we could actually say however many volumes we've used. I'll just call it the Fe for final endpoint. So the volume to get to the final endpoint. And then we're just going to go ahead and solve diluted Kb, or Ka, either way, diluted K for solution. So we would go ahead and say, all right, if I've put in 30 milliliters, and now I'm talking about the 35 milliliter point, 30 milliliters got to me to my final equivalence volume. I have 5 milliliters of NaOH present, or whatever I'm using as my titrant. So now I'll say, all right, I need to dilute my 5 milliliters into my total volume. So the 30 that I've added plus my original volume. I recalculate my final formal concentration, and then I just go ahead and solve for the remaining NaOH. And that's why we're so basic at that point. We're just having a dilution equation applied to NaOH. So those are our regimes of the polyprotic acid-base curve. You'll notice that the monoprotic would look very similar.